Yes, sir.
So last time we were discussed about the continuity of the probability measure from half continuity from continuity from below. Right. So
Yes, sir.
now there is also another important thing. Uh, called it's called the Borel cantilever. So yeah, it's called the Borel cantilever. So, so what does it mean? So yeah, so we'll talk about what does it mean the Borel cantilever. So if you let the sequence of events. So sequence of events. So what does it mean? Any idea?
Like, sir, when we toss a coin, sir, there's a possible of outcomes like head and tails. This outcomes with the sequence maybe.
This outcome?
Outcomes, sir, outcome like all possible outcomes is form a sequence.
Yeah. So no, that's fine. But we have discussed this. What is an event mathematically, right? So what we have done. So we have done so anything omega is a sample space, and then you have f, right? The sigma algebra over omega. Right? So collection of non-empty subsets of omega which satisfy certain properties, those three properties. Okay. So complete omega will be in F. If anything is it's closed under complement and it's closed under countable union, right? So these are the thing, and so these are the F sigma algebra. And anything is an element of sigma algebra is called even, right? And we define probability over for events only. Those things we have discussed. So anything which is a part of sigma algebra is called event. any set which is part of sigma algebra is called even, because you remember that what we defined in the what is a probability measure. It's a map. It's a real valued function from f to 0 1, right? You see, so it's a yeah, it's a map from f to 0 1. That's what we we define that. Uh, it's a map from f to 0 1. Correct. So real valued function from sigma algebra to 0 1 open 0 1 closed interval. So it's a sequence of events, means that AI belongs to F for all I. This means this is the event. Okay. Such that so the probability of AI is finite. So summation probability of AI is finite. This is given that this is given. Then yeah, then then
Sir,
yes.
excuse me, sir.
Yeah. Tell.
Sir, how summation I equal to 1 to infinity probability of all events less than infinity, sir?
This is the condition we assume that
Like,
yeah, tell me.
okay, sir. Uh, these events are from different sample spaces, sir. Like if in one sample spaces, probability of all summation of all event equal to 1.
No, same samples. No, but it's from the same, so it's from the same
Then
omega.
summation.
Same omega.
Oh, then summation of all probability
Uh,
equal to 1, I guess.
no. You are
Then y is less than infinity. Maybe
it's finite.
sir,
It could be one. That's not an issue.
actually I am confused because if in one sem,
Your voice is breaking. Repeat.
okay, sir.
No, repeat. Your voice is just breaking. You come to a good.
Okay.
Yeah, tell me now. Tell.
Okay, sir.
No. So if it is the probability of omega is,
Hello. Confused because sir in all events.
yeah, all events. Your voice is breaking. I cannot hear you. Others can hear him. Others can hear him.
No, sir.
Your voice is breaking, man. So if anyone can hear him, they can repeat the question to me, what he's trying to say. Okay. Or you can
Sir, sir,
put
he is saying the summation of probability should be one, sir. Why it is less than?
probability of omega is one. Okay, that's the convention. Okay. Now now what are the AIs? AIs are element of F, right? Is your F so you remember some examples we did in the we did some examples in each first time. Yeah, you see this example we did. So this is my capital omega, right? And like, this is my capital F, correct? Correct. This is my capital omega, capital F. And what is my event? Event is anything is from this anything from this sigma algebra. Any element from here is called the F, right? So so I have this BC is an element. This is an element here, right? So I have certain things about probability of occurring B and C together. I have something probability of A together, but so probability of events means we are seeing this each of the elements of F, correct? And and it can be something. I mean, I am telling you, summation probability of AI is finite. Probability of omega is one. For this thing, always the for the definition of probability measure, yes. So probability of omega is one, correct? And anything you pick up from F, anything you pick up from F, that's a map from F to 0, 1. Anything you pick up from F, that is from F to 0, 1. So probability of anything you take, probability of so AI is in F, correct? Then this probability of AI, this is some real value between 0 to 1, something between 0 to 1. Okay? It does not. So suppose I choose. So what I have, probability of omega equal to 1 and probability AI is between 0 to 1. And if you have AI pairwise disjoint, then you have this third problem. I mean, it does not say about anything that probability of AI or summation probability of AI will be 1. So for example, I can always make an experiment. I can always make an experiment. Suppose I can always make an experiment that that uh, I can always make some experiment that let's suppose probability of AI. I am playing something, and for each event AI, my probability is 1 by I. Now, this is and I 1 by I says that I belongs to n natural number. Okay. Now, this element is definitely belongs to 0, 1. This is something between 0 to 1, right? I mean, 1 by 1, 1 by 2, 1 by 3. It will go on, right? But what about this series? Summation I equal to 1 to infinity probability of n. Equal to summation 1 by I equal to 1 to infinity. What about this series? What can you say about this series? Is it convergent or divergent?
Convergence, sir.
No, no. How come 1 by n summation 1 by n is a divergent series, right?
Or sequence is convergent. Yes, sir. Yes, sir. It's really divergent.
So the series is divergent, right? This does not converge, right? But I can again redo this example. I can put that probability of AI is summation 1 by I square, right? Then summation, then this is square. And what about this series? Is this series convergent or divergent?
Convergent, sir.
This series is convergent, right? This series is convergent. So this lemma is saying that you have some probability of AI events and such that summation I equal to 1 to infinity probability of AI is finite. This is the given condition. If this happens, okay. I mean, you have some events, and it is not that the summation AI will be 1, never. What the probability measures is probability of capital omega equal to 1. And probability is a map from F to 0, 1. So any probability of AI will belongs to 0 to probability of AI is an element between 0 to 1. So probability of AI is a real number which you can write it like this between 1 to 0. AI is the element of. This is what it says. But if you see
Yes, sir. Now clear, sir.
you see here, so one time if you choose the experiment like that your probability in each time is 1 by I, then it's a divergent series. If you just put 1 by I square or I cube, it's a convergent series. So yeah, so Borel-Cantelli lemma is that I did not complete it. So this is a given condition that that summation AI this is finite. Then uh, it says that then you will have probability of lim sup AI I goes to infinity is equal to 0. Okay. So this is the Borel-Cantelli lemma says that so if AI is a sequence of events such that probability of AI summation is finite. So if this is finite, then this happens. Okay. So yeah, so yeah, so this is the statement of the Bodal-Cantley lemma. Okay. So what is lim sup of a set? You lim sup AI. Any you know the lim sup and lim im definition, right? Correct? So this is the lim sup. Lim sup of uh, this is the definition of lim sup. Lim sup of sets. I mean, if you have a infinite sequence of sets, then lim sup of AI is equal to I equal to 1 to infinity, k equal to I to infinity. So how does it look like? How does it look like? Uh, so k equal to I to infinity, right? First, I can break that. So this means that I equal to 1 to infinity, k equal to, so it's AI union AI plus 1. Right, right. So this is k equal to I to infinity, and I have just written. And what you have I equal to 1 to infinity intersect. Correct? I equal to 1 to infinity intersect. So in a sense, what you have like a one, sorry, intersection A2, A3, intersection A3, A4, A5. Yeah. So what is the intersection will be? I mean, so in a sense that this is a so is this an increasing sequence of sets or a decreasing sequence of sets? Anyone? Is this increasing sequence of sets or decreasing sequence of sets?
So decreasing.
Sorry, again repeat.
Decreasing, sir.
Yes, it's decreasing. It's decreasing because the first one is A1 union A2 union A3. Second one is intersecting with A2 union L3 union A4. Third one is A3. So if you consider uh, if you consider this one, first one and second one, what is the intersection? What is the intersection?
Sir, second one.
Good. And if you consider the first one, second one, and third one, then
Then third one, sir.
yes. So it's a decreasing sequence of sets, right? Because you see, I mean, you first one you have A1, second one is starting from A2, third one is A3. So it is going down the road. So it's a decreasing sequence of sets, right? Correct. So yes, so it's a decreasing sequence of sets. So in a sense that uh, yeah, so in a sense that in this statement, this is also written that so then this probability of I goes to infinity. This is zero. Uh, that is, this means this line, this statement means that no, lim sup probability of lim sup goes to zero. That means that probability that infinitely many of them occur is zero, right? I mean, so that is what I mean. It's a decreasing sequence of sets. So this statement that probability of AI goes to zero. So this statement means that the probability that infinitely many of them occur is zero. So how to prove this? Almost so we will prove it. We have discussed the things yesterday, and we will do it. Do it the same way. There is nothing new about it. Because we have, if you have I mean, decreasing sequence of sets, then yeah, probability of their intersection is equal to that one, right? So we just prove it like that. Yeah. So yeah, we can prove it like that. I mean, it's a proof. So we can define a sequence Bn is equal to right. So yeah, so in a sense, so this is my B1, right? This is B1. This is my B2. This is my B3. Right. So I have defined Bn equal to or, or okay, I can have Bi. I mean, I was doing Bi. Then I. Right. So I have decreasing sequence of sets, right? So in a sense that B1, so B2. And what we have seen from the last class, if you have decreasing sequence of sets, then this happens, right? Correct? This is the thing. So we'll apply this one. So yeah, and so therefore, so implies probability of because I have decreasing sequence of sets, so probability of intersection of Bi is equal to limit I goes to infinity probability of Bi. Right? This is this is my this thing. Correct? Right? Okay. Now, what does it mean? So what I have is probability of intersection I equal to 1 to infinity. Sorry, Bi is equal to limit I goes to infinity probability. Right. Now, what does it mean? What is the left side? So it's like I equal to 1 to infinity Bi. What is my Bi? Bi is this one, right? So it is union k equal to I to infinity ak. That's it. So this is equal to limit I goes to infinity. Okay, okay. Correct. Now this is equal to correct. Correct. Right? Is it clear till this step? Hello.
Yes, sir. Yes, sir.
Yeah. Now we'll use something else, which is like we'll use some property of probability measure, so, which is like this. So what we know, what we already know, if it's a disjoint sets, that if AI intersection AJ is equal to empty set, then summation I equal to 1 to infinity. Sorry. This is we know from the properties of the probability measure. If I equal to AI is disjoint, so there is no then probability of union is equal to submission. Okay. Now, if this disjoint, this condition is not given, okay. If this condition is not given, then probability I equal to 1 to infinity AI is less than equal to summation I equal to infinity. This is called the subadditivity of the probability. So if the disjoint condition is given, then the equality holds. Okay, then you have the equality. Okay, when you have the disjoint condition. But if disjoint condition is not given, then you have these. You have the less equal. I mean, you can just simply draw something and prove it. Like if you have some, suppose you have this thing, you have A here and B here. Okay. Now you see here probability. This is the capital omega. You see here probability of A union B is nothing. Probability of A plus probability of B, because you have a disjoints here. But the moment you don't have it, you have something A intersection. So suppose you have your A, you have your B. This is A, this is B. A intersection B, right? I mean, then Yeah, and you know this. I mean, how you see the these two area. I mean, A union B is like here A plus B, because if you see I mean, you have the whole thing here. So this is your A whole thing here, and then you have your B thing here. So this common area, is coming twice, right? One time with A, one time with B, so it's coming twice. So you have to take the difference once, right? Minus A intersection. So yeah, and you have to take one this thing, right? And and, uh, and this is also some positive thing. I mean, and this is definitely A plus B minus something intersection B is always less than equal to. I mean, if you take the mod here, it's mod A plus mod A. And if you have something intersection, then it is like this. So, this is the subadditivity property of these things, and we will use this here. Okay. So here you have, sorry, I just forward to that. So you have probability I goes to infinity from this is, if you use the subadditivity, it is like less than equal to summation over I probability of A. And this I goes to infinity. Or you can write it like or you can write it like that only. You can write it even whole series. So the given condition is summation I goes to infinity from tail sum. Correct? I equal limit I goes to probability of. Now, if a series is convergent, what you can say about the tail sum? No, summation finite, right? It's given I equal to 1 to infinity finite. Now I have the tail sum. This probability of k goes I to infinity and limit I goes to infinity. So I am going to the tail sum, right? What about that limit? It should go to 0.
0.
Yeah, so it should go to 0. The tail sum, because for a convergence sequence, the tail sum always goes to 0, right? So what I have proved is this limit, this one is equal to is going to 0. So in a sense, and this is my nothing but probability of lim sup, right? AI, I goes to infinity, is equal to 0. That is what we are supposed to prove for Borel calculus. Okay.
Yes,
Yeah.
sir. Yes, sir.
So we take 10-15 minutes break and then we join again. Okay. Okay. Okay.
Yes, sir.
Yes, sir. Sir, please leave to this last second page.
This one.
Yes, sir.
Yeah. Yeah. So line will be on, everything on. I just 10 after 10-15 minutes we start again. Okay? I am not closing anything.
Okay, sir.
anything which is the element of F is called the event. And we have seen that you have R and Borel of R, right? Borel signal algebra of R. Correct? You have seen that, right? So you have real line and you consider all the open sets there or all possible intervals. You consider their sigma algebra, that is the Borel sigma algebra. Or anything is an element of Borel sigma algebra is called the Borel set. Anything is an element of F is called an event, and anything is an element of Borel sigma algebra is called the Borel set. Okay. So, 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 so this function x, okay, x is a omega to r, so x is say to F measurable. The definition is say to F measurable. If I can say or can write it well. So for every Borel set A belongs to Borel set B. So you see, you must so what does it? So X is a map from capital omega to R. So you have here, omega, and you have here F, and you have here R, and you have here Borel sigma. Okay, so for so for any small omega here, okay, uh, so for any small omega, the x goes here and it is x omega. Right? I mean, small omega so here small omega belongs to capital omega, and here x omega belongs to some set A, which is a Borel set, which is so basically, I mean x omega. So A is some subset of R, right? And if you consider interval, any interval is part of the Borel sigma algebra. So A is a element of Borel sigma. Another way of looking at it is and what about this set? What about this set? So what is A? A is an element of Borel sigma algebra, right? So you consider a something here A, you apply the inverse image, X inverse, and you get something here. Here you have A, you apply these things, and you get something here, X inverse A, right? Which is an element of F. Right. So in a sense, I mean, both these things are, I mean, I mean, without for convenience, this whole thing, omega such that x omega belongs to A, this is also simply written that x belongs to A. Simply written x belongs to, simply written. This is the same notation. So or you can write it in this way, x inverse A belongs to. And I mean, if this happens, then we say that this x is F measurable. F measurable. Since from I mean, this is the way we talk about random variable and measurability. I mean, it's, but these concepts are important. Concepts are important. I mean, what we have. Uh, so okay. So in a sense that x inverse of A is nothing but the element omega belongs to omega such that x omega belongs to A. And this is element of F for 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 A. I mean for all A in or I mean A is a subset of. So this is, I mean, this is the way it defined. So this is, so in a sense that x inverse A for A Borel set, this should be a subset of F. And then we call this is F measurable. So is the concept clear? Is it okay?
Yes, sir.
Yes, sir.
So yeah. And so this is the random variable and F measurable. I mean, it's random variable is called F measurable if I mean x inverse A belongs to F for all A in Borel sigma algebra, or you can write this one. I mean, this is the one way. Now another important thing is that another definition. Definition. Sigma field or sigma algebra, whatever you say. Right? I mean, I think we have defined the sigma algebra. Hmm. I think we have defined a sigma algebra, right? So, I just want to see what we have. Yeah. Yeah, I mean, some book it is sigma field, somewhere it is sigma algebra. You can just say whatever. Sigma field. Yeah, it's a notational convenience. So you can have sigma plus sigma field. So sigma field, the sigma field. It's sigma of x. Okay. So this is generated by a random variable x. And and how does it look like? How does it look like? So this concept is very important. This is sigma algebra generated by a random variable. Okay, sigma x. This is the. So we have done sigma algebra for a collection of non-empty sets. Correct. We have done sigma algebra for non collection of non-empty sets. Sigma algebra of omega. I have to finish.
So if for CPDA, CPDA you have to pay and fill it. For project, you don't need it. So project means you take it.
Okay.
CPDA, you have to fill the payment details.
No, not CPD.
You can keep it, sir, for you. Okay. Thank you, sir.
Okay, so what we are saying is that sigma algebra generated by a random variable. So we have done sigma algebra over a non-empty collection of a set. Sigma algebra of a set. I mean non-empty set. Then we have defined the sigma algebra over a set. It should have certain properties. Now we are talking about sigma algebra generated by a random variable. Sigma algebra generated by a random variable. This is little bit more than normal sigma algebra. Now we are talking about the sigma algebra generated by a random variable. Okay. So this is the notation sigma of x. X is a random variable sigma. So what is that? So it consists of all sets of the form where where A is a Borel set, where E is a Borel set in R, or I mean this the same thing, or you can write it is sorry. So in a sense, so yeah, so what we have, yeah, for notation thing, I mean, this whole thing, this omega such that x omega. So this is also we have noted that this whole thing we can shorthand by x belongs to it, right? And that means that x inverse it, correct? X inverse it. So in a sense, what is sigma x by this thing? So in a sense that you are talking about sigma algebra, this is by definition. What is by definition is x inverse of A such that A is element. So this is the sigma algebra generated by a random variable. This is uh, this is an important concept. This is a very important concept. The sigma algebra generated by, so that is what it says, that it is generated by consists of all sets of the form x of A, so where A is a Borel set. So in a sense, the sigma algebra is nothing but it is x inverse A such that A belongs to Borel of R. This is this thing. Okay, this is the sigma algebra generated by a random variable. And another small thing I introduce and then we stop is so 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 suppose you have, it's a, so suppose you have omega, okay, omega, and uh, suppose you have omega, and and uh, and you have a family of subsets of omega. Say you give it some name. U is a family of subsets of omega. Okay. So U is a family of, I'm not talking about that U is a sigma algebra or anything. Okay. I'm just talking about U is a family of subsets of omega. I don't talk about anything more. I don't say the U is a sigma algebra. But what you can do, you can have a sigma algebra, sigma U containing U. And so sigma algebra containing U, and this is the smallest sigma algebra. You can have something like smallest sigma algebra, sigma U containing U. And what is this? We define it as sigma U is the intersection of some sigma algebra such that, so this such that H is a sigma algebra of capital omega such that U is a subset of H. Okay. Now the sigma U is called the smallest sigma algebra containing U, because what is sigma U is the intersection of sigma algebras, all those sigma algebra where U is a subset of those things. Okay? So in a sense that this is also called the sigma algebra generated by the collection of subsets of by U. Okay? So the sigma U is called the sigma algebra generated by those collection of subsets. Okay? So U is a collection of subsets of capital omega. I don't say U is a sigma algebra. I see those sigma algebras which contains U. So in a sense, U is a subset of these things, and I take all of this intersection. That is why this is called the smallest sigma algebra. So this is very important. The smallest sigma algebra containing, or the sigma algebra generated by U, and this sigma algebra is the smallest sigma algebra. So we will use this later, and I just wanted to introduce the definition. Okay. So we'll do some example here and then. Okay, anyway. Okay, so we meet on Thursday, okay? Okay?
Yes, sir.
Okay, so we'll discuss about these things again. We'll meet on Thursday. Okay, thank you. Bye.
Thank you, sir.